As you know, sometimes a polynomial with real coefficients can have imaginary zeros. So it could happen that the auxiliary equation has imaginary roots. And if it does, then the solutions look very different. So if a plus bi and a minus bi are a pair of imaginary roots of the auxiliary equation, then y equals e to the ax sine bx and y equals e to the ax cosine bx are a pair of linearly independent solutions to the homogeneous differential equation. So for example, let's solve y double prime minus 6y prime plus 25y equals 0. So auxiliary equation is r squared minus 6r plus 25 equals 0. I don't see how to factor that immediately, so we use the quadratic formula. R is one of the numbers negative b, so that's 6 plus or minus square root of b squared, 36, minus 4ac minus 100, all over 2a. Now b squared minus 4ac is negative. We're going to get imaginary roots to the equation. So that's 6 over 2 is 3, plus or minus square root of 100 minus 36 is 64. So this is square root of negative 64 over 2, which is 3 plus or minus 64 is 8 squared, so that's 8i over 2. Or in other words, 3 plus or minus 4i. So e to the 3x sine of 4x and e to the 3x cosine of 4x are linearly independent solutions. In fact, they're a basis. They're a basis of the solution space of the equation H. Alright, now let's ask the typical question, which one of those solutions, there's infinitely many, there's a two-dimensional space of them, satisfies certain equations? Which solution has certain properties? So which solution c1 e to the 3x sine of 4x plus c2 e to the 3x cosine of 4x satisfies y of 0 equals 2, y prime of 0 equals negative 2? Alright, y of 0 equals 2 should be easy to analyze. When x is 0, we've got c1 e to the 0th is 1, sine of 0 is 0, plus c2 e to the 0 is 1, cosine of 0 is 1, equals 2. So basically c2 equals 2. All right. Now before I find the derivative, which looks like it's going to involve product rule and product rule, maybe I'll factor out an e to the 3x so that we only have to do product rule once. And since we know that c2 has to equal 2, I'll put in a 2 for c2. So y equals, I'm factoring out e to the 3x, c1 sine of 4x plus 2 cosine of 4x. And y prime equals derivative of the first, 3e to the 3x times the second, c1 sine of 4x plus 2 cosine of 4x, plus derivative of the second times the first. There's the first. Let's see, derivative of sine is cosine, so that's, but then we're going to need to take the 4 out. So that's 4 c1 cosine of 4x. Derivative of cosine is minus sine. So we'll take out the 4 to make 8 and put a minus there. Minus 8 sine of 4x. All right, now y prime of 0 equal to negative 2 implies that 3 e to the 0th times c1 sine of 0 is 0 plus 2 cosine of 0 is 1 plus e to the 0 4 c1 cosine of 0 is 1 minus 8 sine of 0 is 0 equals negative 2. In other words, 3c1, oops, that's times 0, so 3 times 2 times 1, 6, plus e to the 0th is 1, 4c minus 0. So 6 plus 4c equals negative 2. That means that 4c is negative 8, which means that c is negative 2. Oops, well, this is c2. Oh wait, we solved for c2 before. This is c1 where I forgot the subscript. So c1 is negative 2. So the solution is y equals negative 2 e to the 3x sine of 4x plus 2 e to the 3x cosine of 4x. Now the strange thing when the auxiliary equation has imaginary roots is that even though we have imaginary numbers coming into the problem, they sort of quietly go away, and in the end we have only real solutions. So the I doesn't show up anymore at the end of the problem. As much our general solution is all real functions, because c1 and c2 are going to be real numbers. And then the specific solution that had these properties also has only real numbers in it. The end.